The CH-7 program represents a significant and methodical effort in the development of an unmanned aerial vehicle designed for operations in environments where sophisticated air defense systems pose a substantial threat. The project has progressed from conceptual design and ground testing into a crucial phase of practical flight testing, where empirical data gathered from real-world conditions is used to refine and validate the aircraft's systems. The most recent and technically revealing information about this program comes from observations of a flight test prototype, which has been seen operating with an unexpected configuration, the addition of conventional vertical tail surfaces. This deviation from the originally published tailless, pure flying wing design is not an indication of a fundamental design flaw, but rather a clear indicator of the program's current developmental stage and its engineering team's risk-averse approach to validating a complex new platform. The decision to incorporate vertical stabilizers, despite their negative impact on the aircraft's radar cross-section, is a calculated and common practice in the aerospace industry, particularly for initial flight tests of aircraft with inherently unstable or complex handling characteristics. The core aerodynamic challenge of a pure flying wing design lies in its marginal inherent stability, especially in the yaw axis, which is the side-to-side movement of the nose. Without a vertical tail, the aircraft must rely entirely on sophisticated flight control computers making constant, minute adjustments to control surfaces on the wings, known as drag rudders or spoilers, to maintain directional stability. This becomes particularly challenging at lower speeds, such as during takeoff and landing, or at high angles of attack where airflow over the control surfaces can become less effective. The temporary addition of tails provides a robust and mechanically simpler solution to this problem. It grants the flight control system a powerful and predictable means to manage yaw and pitch, effectively damping out oscillations and providing a stable, forgiving platform for the initial forays into the flight envelope. This stability is paramount for engineers to safely collect foundational data on the airframe's structural integrity, its basic handling qualities across different speeds and altitudes, the integration and performance of its propulsion system, and the functionality of its onboard sensors and avionics, all without the added complexity of managing the aircraft's inherent instability. This phase of testing is fundamentally about data acquisition and risk mitigation. The primary objective is to gather a comprehensive set of aerodynamic parameters and systems performance data under real flight conditions. This empirical data is irreplaceable for the process of tuning and validating the digital flight control software, which is the true brain of the aircraft. For the eventual tailless configuration to fly safely, its flight control algorithms must be exceptionally sophisticated, capable of predicting and countering instability thousands of times per second. By first flying the aircraft in a more stable, tail-equipped configuration, engineers can calibrate their models, debug software, and build confidence in the systems with a significantly reduced risk of a catastrophic loss of control. The prevailing analytical assessment is that these vertical stabilizers are a transient feature for these initial prototype vehicles. The operational goal of a very low radar signature remains paramount, and it is anticipated that subsequent prototypes or the final production version will fly in the pure flying wing form, once the flight control system has been matured and proven using the data derived from these early flights. Beyond the temporary tail configuration, analysis of the airframe's physical geometry suggests an evolutionary design process when compared to earlier public representations. Detailed observations and measurements of the test aircraft indicate a wingspan of approximately 26 meters. This is a notable increase from the 22-meter wingspan of the non-flying model displayed several years prior. This scaling of the airframe is a significant design evolution, likely driven by revised performance requirements. A larger wingspan typically allows for a greater internal fuel volume, which directly translates to extended operational range and loiter time on station, a critical attribute for a surveillance platform. It can also accommodate a larger payload, allowing for a wider array of sensors or a greater number of munitions to be carried internally. Furthermore, a longer wing generally contributes to a higher optimum cruise altitude, enabling the aircraft to operate above certain weather patterns and some lower-tier threats, and can improve overall aerodynamic efficiency for endurance. Despite these evolutionary changes, the airframe retains several fundamental design features that are consistent with its stated objective of low observability. The engine air intake is positioned on the upper surface of the fuselage, directly behind the cockpit area. This placement is a deliberate stealth feature, as it helps to shield the highly radar reflective engine compressor fan from direct illumination by ground-based radar systems. The underside of the aircraft appears smooth and continuous, without protrusions, which is a clear structural indication of internal payload bays. This is a non-negotiable aspect of the design philosophy. Carrying weapons, fuel tanks, or sensor pods on external hardpoints would create a significant radar signature, utterly negating the advantage gained by the aircraft's sleek, radar-absorbent shape. All payloads must be carried within the fuselage to maintain a very low observable profile during mission execution. The intended operational doctrine for the CH-7, based on its design characteristics, places it within a modern, networked combat system designed for high-intensity conflict scenarios. Its primary function is envisioned as that of a persistent, penetrating intelligence, surveillance, and reconnaissance asset. It is designed to venture into airspace that is defended by advanced integrated air defense systems, where it would be tasked with locating, identifying, and continuously tracking high-value targets such as fixed command centers, mobile missile launchers, and naval surface action groups. The data collected by the CH-7's sensors would not necessarily be used for its own direct engagement, but would be fused and disseminated in real time via secure data links to a broader combat network. This network could include manned fighter aircraft acting as command nodes, naval surface vessels equipped with long-range missiles, or land-based artillery and missile units, enabling these distributed assets to engage targets with precision at great distances, a concept often referred to as network-centric warfare. Beyond this primary sensor role, the platform's substantial internal volume and capacity for electrical power generation make it a plausible candidate for electronic warfare missions. These could include passive signals intelligence, where it listens to and geolocates enemy radar and communication emissions, or active electronic attack, where it uses powerful jammers to disrupt or deceive enemy air defense radars. The observable progression of the CH-7 into a flying testbed, even in this instrumented and temporarily modified configuration, signifies a concrete and advanced transition from theoretical design and ground-based testing into a critical phase of practical validation. This phase brings the platform closer to being a potential operational system that could, if successfully developed and deployed, alter the tactical and strategic calculations in regions characterized by advanced anti-access and area denial capabilities.